Here is an example of impact between two objects. It's a very simple example. I have two balls. One is 2 kilogram, the other one 1 kilogram. Both of them are traveling at the same velocity toward each other. And the coefficient of restitution is half. We want to find the final velocity of each ball after the impact. So this is a classic impact problem. The line of contact is the same as the direction of velocities, so it's not an oblique impact. So let's see what we have. We know, well, this is also as many problems we have seen so far, this is a multi-state problem, multi-state and multi-phase. You have before impact, during impact, a lot of things might happen, and after impact. What we are really interested is right before impact begins and right after impact ends. So my state one, it is right before impact, right before impact. I know the two velocities. VA1 is 1 meter per second. For convenience, pick at random one positive direction and stick with it. And VB, I'm going to write two objects in the same line. VB1 is -1. I don't know any other information about the states of these two objects other than the speeds. I don't know where they are. I don't know any information about time. So that is really all I know. State 2, which is right after impact ends, VA2 is unknown, VB2 is unknown, which coincidentally is what the problem is asking. So let me write it here. Where is it red? What I need to find is VB2 and VA2. So these are what I need to find. And so the question is, that is all the information given. The only question remains is, how does this transition from state 1 to state 2 look like? I have another piece of information. I know coefficient of restitution is half, whatever that means. And yeah, that is all I know. I'm not going to draw it, but assuming this is an impact, I can ignore all other non-impulsive forces on the bodies. So the only main force acting on the bodies during impact, during this transition from state 1 to state 2, is the internal impact impulsive force between the two bodies. So from outside, looking at both bodies together, there is no external force during that very short amount of time. So from here, linear momentum is also conserved. And so these two pieces of information are likely what you need to go from known initial velocities to unknown final velocities. So solution. So we have two known pieces of information about the transition. Let's start with one of them. Let's start with known information 1. I know it is useful because coefficient of restitution is related to final velocity. Somehow the final velocities show up in that equation. So E is essentially relative final velocity, relative initial velocity. So VB2 minus VA2 divided by VA1 minus VB1. So the top part is what I'm looking for. The bottom is I have, and this one equals half. So from here, I know VB2 minus VA2 equals half VA1 minus VB1. So relative velocity decreases by half. And the other known information about the transition is conservation of linear momentum. So MAVA1 plus MBVB1 equals MAVA2. Oh, I didn't write this. Let me write it down for completeness. MA equals 2, MB equals 1. So if the information is not there, well, how are you going to use it in your solution? So information must be there. So I have everything VB2. Left hand side is fully known. Right hand side has the information I'm looking for. Let me finish this. This is half times VA1, which is 1, minus VA2, which is 1, but in the opposite direction. So this is 2 equals 1. Right? Yes. And here MA2 times 1 plus 1 times minus 1 equals 2VA2 plus VB2. And 2 minus 1, this one is also equal 1. So my equations are relatively easy. I have 2 equations and 2 unknowns. Either one of the 2 is not enough to solve the problem. I need to have both. So I have these 2 pieces of information. Let's take from the top one, find VB2. VB2 is 1 plus VA2. Plug it on the second one. 2VA2 plus VB2, which is 1 plus VA2 equals 1. So here I have 3 VA2. What? Plus 1 equals 1? Apparently. 3VA2 equals 0. So I wasn't expecting this. Double check my calculations. Hopefully it is correct. So VA2 equals 0. Interesting. With the numbers I have chosen at pseudo-randomly. Apparently VA2 turns out to be 0. So after impact, A stops and B bounces back. So I can calculate VB2 is 1 plus VA2, which equals 1 meter per second. And it turns out positive. So V bounces back in that direction. and VA stays still. Interesting. Very happy coincidence. I wasn't expecting. Let me just double check if the momentum is the same. We have two that way. Well, yeah, okay. Interesting. Good. Yeah, all of it good. So that is a happy coincidence that after the impact, A stays stationary, so B has essentially enough enough momentum in it to fully stop A, and in this process it is bounced back with a velocity equal to 1 meter per second. Okay, this is an example on impact and how you can use the known information about coefficient of restitution to find velocities after impact. And yeah, I leave it here.